In the beginning, there was light. For countless ages, the light shone, and it shines across our night sky still. The light of stars, nature's way of releasing vast energy. The light of fusion. Man reached out beyond his own planet into space and began to understand the laws of nature, the laws of physics, which govern everything. He even began to understand the inner workings of stars. Our own star, the sun. A massive ball of hydrogen gas, collapsing under its own immense gravity, with enormous pressure at its core, and heated to millions of degrees. Our sun has burned for over 4 billion years, and is likely to burn for as long again into the future. Throughout this time, like all stars, the sun has radiated immense energy in nature's chosen way, from the fusion of atoms of hydrogen. Driven together with immense force at the sun's core, they change to helium, releasing energy, which has shone out across space for billions of years. Nature's own energy source, fusion. Today, we face a huge challenge: to find a new way to satisfy our ravenous demand for energy. Scientists are pursuing a solution to produce the energy we need without making even more carbon dioxide, or the enduring legacy of long-lasting radioactive waste. They seek to unlock the immense power of the atom, not by fission, which tears atoms apart, but in nature's own way, fusion. The power which drives the sun itself. For many years, scientists have been developing the technology to unlock fusion. The most advanced approach uses powerful magnetic fields. In 1997, the European Jet Facility in England achieved 16 megawatts of fusion power. And now, the international ITER project seeks to advance that achievement towards 500 megawatts. Fusion power on the industrial scale. The magnetic approach to fusion is exciting and is making real progress. But the scale of the energy challenge demands multiple and complementary solutions. The potential of lasers to unlock the power of fusion has been a vision ever since their invention. Now, in the 21st century, the proof of principle for laser fusion is about to be achieved. With billions of dollars invested in the construction of the National Ignition Facility in California and the Laser Megajoule in Bordeaux, the largest and most powerful lasers ever built. Yet much has to be done before we can fully reap the benefits, for fundamental science and for developing a fusion power source. Scientists and funding agencies across Europe have come together to face this challenge An ambitious pan-European project is now underway to provide the evidence that a laser-driven fusion reactor could be a source of secure, abundant energy and a unique resource for fundamental science. This major step is the goal of the High-Power Laser Energy Research Facility, HIPER. The world is facing hard realities about our future energy needs, and it's essential that we should have as many solutions as possible to meet this challenge. As American and French scientists approach proof of principle for laser fusion, HIPER will be ready, a project timed to take this new knowledge forward into detailed development, providing the scientific basis for a viable laser fusion reactor. A major driver for the HIPER project is the scientific impact of being able to generate here on Earth some of the most extreme conditions found anywhere in nature. HIPER will recreate pressures and temperatures only to be found at the center of the Sun or in an exploding supernova. This critical step in physics underpins the HIPER project. Alongside the scientific challenge, bringing together all the technologies for HIPER will be a major undertaking of engineering and construction in a building the size of a cathedral. Here, science teams will prove that through controlled fusion, we can unlock the vast energy of the atom. In the HIPER building, the banks of lasers will fire intense light pulses, which are amplified and shortened, then fed into a vacuum chamber to trigger fusion in a tiny pellet of fuel. Huge power will be focused onto the fuel pellet in the chamber, with 2 laser shots, each lasting a tiny period of time. The process begins. The lasers fire, and pulses of light pass through the complex system of optics and laser amplifiers. By the time it leaves the laser, each pulse of light carries energy compressed into a billionth of a second and focused into a beam just 1 millimeter across. The light pulses are split many times, and each one is amplified. Then they're distributed around the outside of the fusion chamber, entering it from many angles. The cycle is started when a single fuel pellet is fired into the chamber at high velocity, and the laser systems will track it, firing 2 timed pulses to strike the pellet precisely as it reaches the central point. As the target is struck by the first set of pulses, the impact vaporizes the pellet's casing, driving a powerful shockwave inwards and compressing the fuel to a high density. At the instant in time when the pellet's core reaches maximum density, a second and even more powerful laser system fires one much shorter and more intense pulse in a beam finer than a human hair. In just a trillionth of a second, it raises the core's temperature to the point at which the fuel lights, and fusion begins. More than 100 million degrees. The nuclei of atoms do not naturally touch, always repelling one another. But forcing together the nuclei of 2 hydrogen isotopes overcomes their natural repulsion, causing them to fuse and form helium, and an escaping energetic neutron. This unlocks the huge energy which binds together the nuclei of hydrogen atoms. Most of this energy concentrates in the escaping neutron and can be captured to superheat water, drive a steam turbine, and so generate electricity. This can be seen as mass converted into energy, a real demonstration of Einstein's famous equation, the product of one brilliant mind a century ago, tapping into power which has been stored within atoms ever since they were created. Controlling fusion is attractive, but also challenging. Finding the solutions will push science and technology to new limits. The HYPER project is not a short-term undertaking, but meeting the energy challenge makes it well worth the effort and the cost. We need a reliable way to deliver energy on the mass scale without burning our limited resources of fossil fuels and without the problems of long-lasting radioactive waste. We also need energy security, with fuel supplies readily available to all nations. Only fusion meets these demands. It produces no carbon dioxide, burns no fossil fuels, creates no long-lived radioactivity, and uses a fuel which will last for the very long term. That fuel can be found in seawater, something which, thankfully, we have in abundance on Earth. Just 1 cubic kilometer of seawater contains the fusion energy equivalent of the entire world's oil reserves. It sounds almost too good to be true, but nature does not give up her secrets easily, especially secrets of such immense power. To control fusion will require a great effort by our brightest scientists and long-term commitment between nations. Only 2 approaches seem set to conquer fusion, each with its own advantages and complexities. Magnetic confinement is approaching a scientific solution at industrial scales of power, whilst laser fusion is set to demonstrate proof of principle near the turn of this decade. These techniques offer real hope that mankind can harness nature's primary energy source. Using powerful lasers, the HYPER project is Europe's answer for one of these approaches. A collaboration of European nations with support from countries across the globe, HYPER brings with it huge potential for pure science and has begun preparing the way to meet the challenge, to master controlled fusion, to study the path to abundant, clean energy for the future.